All right, let's go. Week 9, Wednesday. So today I'm going to do more linked lists. Take a look at two different views of linked lists. And part of what I'd like to do today is convince you that recursion leads to some really nice solutions. So we'll talk about a recursive view of lists later on. I wanted to finish off the kind of view I was taking on Monday. So don't forget, if you're scheduled for your second round of prac exams this Friday afternoon, you're on. Don't worry if you don't perform too well. Andrew's been telling me that some students think, oh, we failed this prac exam, so we're going to fail the course. No, you're not. It's only worth 10%, and you get another chance at demonstrating that you can manipulate arrays in the final exam. And if you do that, no problem. You still lost the marks that you didn't get in the prac exam, but as I said, it's only 10%. Of course, that's the difference between 55 and 45. So I shouldn't say just 10%. Right, so that's Friday. Sunday, Andrew says he's going to have the assignment up. It's not going to be Knowledge Island for people who know about that, but it's some kind of gamey thing. He hasn't told me exactly what yet. Next week we'll be talking about abstract data types, and I'll kind of allude to that a little bit today. For enrolling next semester, this week is when enrolment's open and you get your so-called, what do they call them, appointments or something like that. Anyway, if you're a CSE major, pay a lot of attention. If you're not a CSE major but you really like COMP1511 and you want to do more computing, you might want to pay attention as well. So these arrows represent prerequisite relationships. So you can see COMP1511 is the core, everything starts from COMP1511. So that's an important reason not to fail COMP1511, because that's going to slow you down a lot, because you can't really do anything else until you've passed this. And it's important to build those foundations anyway. All right, so 1521 is the brand new, not the same as COMP2121 as rumours seem to be going around. It's a computer systems course, talks about a bit about assembly language programming, a bit about structure of operating systems, networks, and so on. And that leads on to all of the hardware courses like COMP2121, if you've looked at that, operating systems, networks, and so on. COMP1531 is the new core software engineering course, dealing with teamwork, building a little web app is the goal at the end of that course, learning a bit about databases to the point where you can have a database backend behind your web app, and so on. COMP2521, and you may notice that the only prereq for 2521 is COMP1511, so in theory you could take it next semester if you really wanted to. If you really want to max out your computing, you can take all three of those next semester because they're all running. 2521 is the data structures and algorithms course. Vaguely, it'll be a slightly ramped up version of the old COMP1927 if you know about that. 2511 doesn't run until next year, and the current equivalent of that, COMP2911, doesn't run in second semester anyway, so you don't have to worry about that particularly. COMP2041, if you seriously want to max out on computing, you could take all four of those courses in semester 2. Not sure why you would. Some of you, I think all of you would have to take a bit of maths as well, but if you really want to, go for it. COMP2521 is turning into a bit of a bottleneck. A lot of the later courses have that as a prereq, so make sure you do that reasonably soon. All of these courses are going to be offered in, and that one going to be offered in both semesters next year. Once we hit trimesters, I don't know what we're going to do. 2041 is only offered in semester 2, so if you're really keen on it, it's about Perl and Python and implementing software without writing programs, essentially. So you can do shell scripts and so on and so on. It's quite a useful course. It doesn't directly lead on to anything else in the same way that 2511 and 2521 do, but it's still a very useful course. And it is core in some of the programs. All right, any questions on that? So think about that when you're enrolling. Hopefully that's helpful to some extent. All right, let's get back to linked lists. All right, so a linked list consists of a whole bunch of nodes. Oh, and no, and Andrew decided he didn't like the data structure we used last week, on Monday, so he wanted to rephrase everything like that. He's decided type defs are evil for some reason, and we're much better off being upfront about the fact that a node is a struct. So rather than writing list node like we did last time, we're going to ditch the type def and just write struct or node everywhere. It's the same thing. Alright, so a list is represented by a pointer to the first node in the list. A list consists of a series of interlinked nodes that are linked together by a next pointer. You allocate nodes by malloc, and the last node in the list always has a next pointer, which is null. And if the list itself is null, it means the list is empty. Alright, so let's continue on with this. We've done a lot of stuff, so alright, so let's back up. So I got rid of that type def, and I'm doing everything in terms of struct node now. So a node contains data and next. Checking whether a list is empty, pretty straightforward. You just check whether the list pointer that you're given is null. And as I mentioned, you could always do it as a one-liner, okay, with that line there, but the standard way of doing it is probably like that. We need some kind of function to create new nodes. This function takes a value, which is the thing that's going to be stored in the data field of the node, and it takes a pointer as an argument, which is the value that's going to be stored in the next field of the node. You can see that down here. And of course, malloc may fail, unlikely unless you've got a program that's allocating tons and tons of memory running for a long time, and you might chew up all of the available memory, in which case malloc will fail. So it's remotely possible that you might bump into that error sometime. Generally, bumping into that error is generally a symptom that you've screwed up something somewhere else. So you might be doing lots and lots of mallocs and not freeing up the memory that you allocated. So you're just accumulating more and more alloced memory that can't be used for anything else. Whereas if you'd freed it, it would be available again. Inserting a value at the front of the list is dead easy. You simply create a new node. In that node you store the value that we're trying to insert, and you simply, the next pointer is simply a pointer to the node that was the first node in the list and has now become the second node, and then the new node in the list is the new first node. Notice that all of these functions, or most of these functions, tend to return the new version of the list. So they take in the current list and they return the modified list. So in this case we're returning a pointer to the new node that we just created, which is the new first node in the list. Getting a pointer to the first node in the list is dead simple. You simply return that. Getting a pointer to the last node in the list requires us to use a standard list iteration technique to go right to the end of the list. It's generally useful to handle the case where the list is empty, because otherwise that makes the rest of your code messy. If you get that out of the way, notice I've been naughty here, I've stuck it all on one line. If I was remotely following Andrew's coding conventions, then I would have done it like that, and I would have put braces here as well. But in any case, current starts at the start of the list. we iterate until, in this case, we iterate until current next is null. And the reason we're doing that is we want to stop at the last node. How do we know we've reached the last node? Well, I said in the description of the list that the last node always has a next pointer which is null. So that's what we're looking for. As soon as that condition's true, we know we're at the last node, so then we can return a pointer to that node. If we haven't yet reached the end, then we move on to the next node in the list using this standard list traversal strategy. Appending an integer to the end of a list, all right? Once again, handling the empty list case is usually a good idea. Get that out of the way and then worry about what you do if the list isn't empty. If the list is empty, then we can just use insert and create a new node, stick it at the front of the list, which currently has nothing in it. Otherwise, we do something like what we did in the last function. We scan to the last node, we create a new node, we make it the last node by putting a null in its next pointer, and we make the current last node, which currently has a next value of null, point to the new node. Right. There's a whole bunch of diagrams, they're all sitting under the desktop /week09 directory. You can have a look at them to show how this all works. I'm not sure why I got that code there. Oh, maybe that was to show that doing this return up here means you don't have to, the code isn't as deeply nested, so in theory it's less complicated. Printing the contents of a list. Okay, once again, we see the standard list iteration pattern. Go to the start, go to the end, and advance from one node to the next, using that statement there. The only complications here is that we have to wrap up the values in square brackets, and we have to make sure that when we reach the last node, we don't print a trailing comma. So that's what that's all about, but otherwise it's standard list iteration. Here's an even more simple list iteration, and I've rendered that as a for loop. You could write it the way I've written it down there, which simply counts the number of nodes as we traverse the list. Some you could do in exactly the same way, except you grab the data values and you incrementally incorporate them into some variable, which you initialize to 0. The nth pointer in the list, we simply use a for loop to iterate that many times over that many nodes, and we stop once we reach the nth node. This one looks buggy to me. Why might this be a problem? Now notice we've handled the empty list case, that's fine, so we're not going to have a problem there. But when might we have a problem? Imagine that there are 5 nodes in the list and we ask for the 10th node. Execute this in your head and see what's going to happen. So we start at the start of the list. We're going to count up to 10. On each iteration of the loop, we advance to the next one. So starting from the first node, we go to the second node, we go to the third node, we go to the fourth node, we go to the fifth node. When we're on the fifth node, we're still counting the index variable upwards, and we're going to say current is assigned current next. We're on the last node, so what value is current going to get? It's going to get the value null, but the loop hasn't finished, so we're going to go around the loop again, and we're going to try and evaluate this expression with current set to a value of null. As soon as you try to dereference to a null pointer, you're going to get a segmentation fault and your program will crash. Okay? So if I is larger than the number of elements in the list, this function here fails. So we really need an extra check in here just to make sure that we haven't fallen off the end of the list. And if current We definitely don't want to do that, and we probably want to return some value right at this point, and the only sensible value I can think to return is null. So it's kind of saying there is no nth node in this list where n is larger than the largest index value. So I would suggest that this would be an appropriate way of handling an index value that's larger than the number of nodes in the list. And of course, I'd better add that. Right, so you need to be a little bit careful about pointers becoming null because you've gone too far along the list. As soon as you reach the end of the list, the typical pattern for checking that is something like this up here. So as soon as current is null, we stop trying to go further along the list. In this case, the loop isn't controlled by the fact that current is not equal to null. That'd be another thing that we could do. We could actually add current not equal to null as part of their test here. So while I is less than index and current not equal to null would be a way of dealing with that. But in any case, at the moment, the way it's expressed here, the loop is controlled by changing I. It's not controlled by checking whether we've reached the end of the list. So we need to add an additional check in there for that case. Right, so that's the nth node. If you want to get the middle node, we just work out the middle index and then grab that one. Checking whether the list is in ascending order. Alright, well this is something that we haven't implemented yet, so let's take a look at that. How to do that? Well, one way you can start by thinking about this, and this is true in general, think about the possible cases that we could have that are interesting in terms of this functionality. You know, or I've been hammering away at the fact that we treat empty lists differently. So that's one case we can worry about. In the case of is ascending, what we're interested in checking is that if we take a pair of adjacent items, the one earlier in the list is smaller than the one later in the list. And that property has to hold for every pair of items all the way along the list. So the first item is smaller than the second item is smaller than the third item is smaller than the fourth, and so on. Alright, if we've got an empty list, then that condition is not violated, so we could say that by default an empty list is an ascending list. So we can return 1. Right, now, in all the examples I've looked at so far, I've kind of treated the empty list as a special case and everything else has been handled in the rest of the code. I'd argue that there's another special case here, which is the case with one element in the list. Okay? So we can check for that case, and in that case, once again, as for the empty list, the sortedness property isn't violated because there's only one node, therefore you can't have nodes out of order. So in that case, then it's also true that the list will treat the list as ascending. And how do we recognise the case where there's one node in the list? So we give a list which is pointed to the first node. If the first node has a next pointer which is null, then we know it's the only node in the list. So in both of those cases, either a list of length 0 or a list of length 1, we say that the list is ascending. Now of course there's another way we could have done that. We could equally well have written that, because we've already got a function that will compute the length of the list. And if the length of the list is less than 2, then that's also the case. But interesting thing about function calls are extremely nice from a programmer's perspective, from a program performance perspective, making too many function calls isn't a great idea. So if you can avoid making a function call in a nice simple way, like we've done here, that's pretty straightforward to work out what that expression is doing, then it may be better to do that than make a call to a function. Alright, so we've handled that case. Alright, so now we know we've got a list which has at least 2 nodes in it. In fact, I don't need anything else because I've got a return. Alright, so everything I write here will only happen if we don't return 1. Alright, so what we need to do, scan along the list looking at adjacent elements. So we need to have a current element and we need to have a current next element, if you like. And we're looking at those two, and they move along together. In fact, we don't even need 2 pointers, we can just have a single point. So we move current, 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 and the condition for stopping moving along is when we don't have any more. We don't have a pair of elements, so that current next is null. It means we're at the last node, there's no following node that might be out of order. So, like those other ones, we're stopping when we reach the last node. Oops. And you might say, if this was a pantomime, hey, you haven't defined current. Were you about to say that? No? Alright. Well, I haven't defined current, so I should define it now. And it's a node pointer, like it was in all the other functions up above. Right, so what do we need to do? We need to check that the data value in the current node is less than the data value in the next node. And if that condition holds, then we keep checking. And all we need to do is find a pair of nodes where that condition doesn't hold, where the earlier node is larger than the second node. And in that case, we know the list isn't sorted in ascending order. Now here we're assuming that we're going to allow duplicates in the list, and if we have duplicates, we'll treat them as being ordered. So it's kind of not strictly ascending, it's kind of not descending, if you want. Is in ascending, maybe I should change that. Right, non-descending order. So, all we need to do is find a counterexample to the fact that it's in ascending order, and the way we can find that is if we look at the current, if we look at the current next data item, so the data item in the next node, and we compare that to the data item in the current node, and if the item in the next node is less than the item in the current node, then we know we're out of order, or we're not non-descending. So as soon as we find a counterexample, we can return fail. Otherwise, we just keep ploughing through the list in the usual manner. And if we eventually reach the end of that while loop, it means we checked all adjacent pairs of items in the list, and all of them were in order, therefore the whole list must be in order. So if we reach this point in the function, then we return 1. Right, any questions on that? Now, if you want to have it strictly ascending, and if you don't want to allow duplicates, so if you've got 7 followed by 7, then we say that's not ascending. The way to deal with that is very straightforward. You simply change that from less than to less than or equal to. Okay, so we don't allow 2 adjacent items to be equal, and and we certainly don't allow the following one to be larger than the preceding one. So, any questions on that? Alright, let's check whether it works. So that program is listed. Well, what do you mean it's up to date? So I just saved that. Oh, I didn't. Okay, interesting thing. So, what make does, it compares the time that files were updated. And last 0.c, I hadn't saved that from the editor, so it still had the old version of last 0.c. That old version was the one that was used to create the current executable list 0. So as far as make is concerned, list 0 is up to date because it's newer than the source code. If I go and save the file, you can see the little star up there which tells me I haven't saved it. If I save that, I've updated list 0.c, and make will recognise that and then do a recompilation, and even better, good and it will tell me I've got some errors. Alright, current is blah 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 blah. Oh yeah, good point. Why didn't someone yell out, you've forgotten to initialise current? And I would initialise it to list. So current starts out pointing to the first node in the list. So once again, I've got to save and run make again. Notice the only thing I did there, interesting, current is uninitialized, blah, 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 whenever this if condition's false. Alright, so it might look like it's telling me there's something wrong with that. In fact, there's nothing wrong with that. The problem is that if that test fails, in other words, if the list has at least 2 elements in, then I'm going to have a problem with an uninitialized use of current. Alright, so if I do make, beauty. Alright, what's the problem now? Oh, look at all of those. What did I just... Oh, I did. Oh, okay. I tried to make the other program that I haven't written yet. Alright, let's just make list 0. Okay, so it's happening to that. Yeah. Alright. Enter a number. 3, 4, 5. That'll do. That's a list, it's got 3 elements in it. They're in ascending order. The first element is 3, the middle element is 4, the last element is 5, and that's what all of this stuff that's about to be written should tell me. Right, list is 3, 4, 5, first element 3, last element 5, middle element 4, list, length of list is 3, sum is 42, well it's not because I didn't write the sum function, I was leaving that for you to write, and the list is in ascending order. Alright, let's try a list that's not in order. And it tells us that the list is not in ascending order. Okay. Let's see what happens. We're not finished, of course. There's still a lot of other cases to test. Let's see what happens if we don't enter any numbers. It tells us the list is empty and stops. It doesn't try to execute the rest of that stuff. What about a list with just 1 number in it? Well, it tells us that the list the length of the list is 1, that's what the list looks like. First, last and middle are all the same, there's only 1 element. That's good. And the sum of the list is not 42, but the list is treated as being in ascending order. So we're happy with that. Are we done? What else can we test? Try something larger with duplicates. So under my definition of ascending, which is really non-descending, that list is in order. Notice that you're allowed to insert duplicate values into the list. First one is 1, the middle element is 2. Most likely it grabbed that one. Yeah, it did grab that one. because there's an odd number of elements in the list, so that would come out as the middle. And the length of the list is 7. Alright, so it looks like list 0 is working okay, that program. Alright, so we'll stop playing with that and we'll go on to a different implementation of linked lists. Now this one I've tried to do the lists as a library. So there's a .h file that tells me what all of the functions on lists are. There's a main program that uses those functions, and it's called list for linked lists. And there's the actual implementation of all the list functions called lists.c. Where's that? There. Alright, so let's take a look. So the linked list data type, right, we saw that before. Oh, there's a bug. We didn't see that before. I had to go and change all the data types just before the lecture, so to fit in with what Andrew wanted. So I haven't necessarily got everything right. Hopefully I have. No, I don't. Look at that. What a mess. I can't just write node star here because there's no such data type as node. So everywhere I've got node, I really, I don't want to do that. Everywhere, come on. Oh, that's right. I'm not using VI. That's unfortunate, so I have to do this the hard way. Everywhere I've got node, I should have had struct node, which is the actual name of the type. Oh, I should have used substitute, yeah, find and substitute. Anyway, I didn't, so now it's all done. Alright, so we've got a function called showList, which is going to display the list in a different format to what we previously looked at. Length, we already had in the previous example. Search, we didn't. So what this function is going to do, it's going to scan through a list, take a particular value, integer value, and see if that value appears somewhere in the list. Is sorted, that's basically the same as is ascending. Insert is going to insert an element at the start of the list. Append is going to add it at the end. We've already seen those ones. Delete is going to remove an element from a list. So if we've got a list, blah, 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 and we've got the number 8 in the middle, and we say delete 8 from that list, the new list is going to look like the old list, except that element, the node containing 8 will be gone. And we've also added a new function to completely free up all of the memory that we allocated to the list. So if you're using a list in your program and you only need it temporarily, you don't want to leave it hanging around after you've finished with it. Remember that all of these list nodes are malloced. So unless you explicitly get rid of them, they're going to hang around occupying memory. So free list is something that's going to clean out all those nodes and restore all of the memory that was being used for that list to be available to be re-mallocked sometime in the future. So that's all the functions. The main program behaves like this. So it's a little, if you like, command interpreter. It gives you a prompt. You can ask, what can I do? How do you do that? You just type some rubbish and it tells you it's an invalid command, and it gives you the list of all the things that you can do. So you can insert a value at the start of the list, you can append a value at the end, you can delete from anywhere in the list, and you can check whether a particular value is in the list, show the length, check whether the list is sorted, just print it out or free it up. So let's build a list. So we can insert one. So this is the format that showList produces. And we can append, and we can append again, and we can append again, and then we can check the length. it'll tell us the length is 4, nice. We can say, is 5 contained in the list? No, it's not. We can check whether the list is sorted. Yes, it is, and so on and so on. Right? We could also delete things. So if, let's say we want to delete 3. So now we've got the list just 1, 2, 4. Okay. And if we check the length of that, then we see it's now 3. And if we try to find 3 in the list, it ain't there. It's just gone forever. Alright, so we've got this little command interpreter that'll sit there reading these simple commands and doing stuff, manipulating a list. So it's a little bit more flexible than the previous program, which just ran through a set of tests. Now we can do more extensive tests, and we can do them interactively. The other thing it does, it'll let you delete the entire list. No, it won't. Well, it will, but it's not called D, it's called F for free. Right, so now the list is completely empty, and if we want to check its length, we find that it's 0. More importantly though, all of the memory that was allocated to this list up here is now freed up and available for use. Alright, so the other thing we can do is we can quit. So, let's have a look at the main program, which may contain something interesting. I don't know. Right, so the main program simply reads commands and executes them. Obviously it has to interpret, so the commands are simply text typed on the line. The program has to interpret that text, and I've used an extremely simple structure for these commands, so they're easy to interpret. Alright, so we've got a bunch of data structures. The main one up here, list node, no longer exists. Oh dear. There's something else that needs changing. It's probably why we got so many compilation errors before. Right, so keep it neat. So list is the list. So this thing manipulates one list, and that's all it does. Allows you to add stuff in, take stuff out, and so on. Right, all of this is for dealing with the commands that you type in. And these are, well, that too. And this is used for controlling whether the list is displayed or not after a command is executed. So if a command like, length doesn't change the list, we don't bother printing it each time. Alright, so we create an initially empty list, which we do simply by setting the pointer to null. And then we read and execute commands. Right, so we print the prompt, we read in the next line of user input, and we try to understand it. And the way we understand it is very simple. We just use scanf. So this fills up the line buffer with whatever text the user types. If you remember last time I said buff size was a predefined constant that's defined in standard io.h. It's just a large number that you can use for creating string buffers that are unlikely to fill up. And you may have noticed that I used it up here to create, to define the line buffer. Alright, so fgets reads from standard input into this line buffer, and it won't read more than that many characters, so we're not going to overflow the buffer. Alright, we're assuming that we're not going to change the list while we're executing this command. What is this command? Well, we work that out by doing an scanf, looking at the text that's contained in the line. Remember that scanf operates on a character array using the normal scanf formatting conventions. So what this is going to do, it's going to look for a single character followed by a decimal integer, and it's going to store those values in the variable command and the variable value. And then we've got, if we type A5, then command is going to have the value 5, the value A, and val will have the value 5. Alright. And the other thing that we do, we just remember how many things we actually managed to scan, because you may have noticed that some of the commands require an argument, like A3, and some, like hash, don't require any argument. So if the command is A, we got to make sure that there was a second argument, which is a number. If that's not the case, then nargs is not going to be equal to 2. It might be equal to 1 because the user typed A on a line. So if I just type that, command will get set equal to A, and val will not be set to anything, and the value that's returned from scanf is going to be equal to 1. I managed to read a character, but I didn't manage to read a decimal integer. Therefore, that's an invalid command. Whereas if I type append 1, then that actually works. Alright, so we check if the command is A, that there is a value that's been supplied, and then we append that to the list. And we indicate that we actually changed the list. So similarly for insert, there has to be a second command line argument, then we use that to insert that value into the list and indicate that we changed. Deleting, once again, there has to be a second command line argument, so that'll be contained in val, so then we'll try to delete that value from the list. If the value is not contained in the list, then delete should not have any effect. So we just leave the list unchanged. Searching for a value in a list, we have to supply a value to search for. So once again, narg should be equal to 2. This time we call a search function, and if we find that particular value in the list, we print found, otherwise we print not found. If the command is s, we call the sorted function. If the command is hash, we call the length function and use that to display the length. If the command is f, we call the free list function, delete the list and delete all of the memory in the list. Notice that simply deleting or freeing all that memory doesn't actually change the value of list. I don't know where L came from. Doesn't change the value of list. So the list would still be pointing at the memory that was formerly occupied by the first node in the list. So you shouldn't leave that situation set up. You've got a pointer pointing to some memory that was once mallocked that has now been freed. So as far as the rest of the universe is concerned, this memory is not in use. So the address in here is an invalid address. C doesn't understand that. It'll keep the address hanging around. So you really need to make sure that you explicitly set that to indicate that there's nothing left in the list. And of course, doing that obviously changes the list. P prints the list, so we fudge that simply by saying, oh, the list was changed, when it actually wasn't, but it will force the list to be printed. And Q quits from the program, so we actually break, and that break statement there is going to jump out of this while loop. So two ways you can exit the while loop. You can either go through that break there because you typed an explicit Q command, or you can just stop typing input. So if I type Control D, then the program stops. I can also type Q and the program stops. Alright, and at the end we actually free up the list. And if we'd already freed it, this will be a good test. That's the old version of free list. This will be a good test that freeing an empty list doesn't cause any problems, because it's always a potential case where things can go wrong. Try to free a list that contains no values. Right, and then we print a new line and we return. Right, so there's the thing that prints the help message. So that's the main program. Might be slightly interesting to have a look at, so you can see how, you can write a command interpreter. All this is really doing, it's just reading a line of input and from that line of input working out which of the list functions should be called. Alright, so let me see what's the time, 11:53. Alright, so here we've got our lists.c, which is all the implementation of all of those functions. So in lists.h, we've got the interface to describe how all the functions are used. Oh, the other thing I should have pointed out, in list, right at the top here, we do a hash include of lists.h, which means this program now knows all about those functions, or at least it knows what the interface is, so what arguments it should give, what parameters it should give, and what kind of return values it's going to get back. It doesn't actually see the functions though, they're contained in the lists.c file, alright, which is here. Right, so one of the functions, it's like, I think in the previous example it was called create node, and in the previous example we actually had 2 parameters. Here we've only got 1. So this version of creating a node calls malloc, and it does that check to make sure that malloc worked. That I keep changing the names of all these functions. Alright, so it prints an error message and then quits. Otherwise, it sets the data value to whatever was passed in, and it always sets the next value to null. So it's really going to be up to the calling program. If it wants to set next to something different, then it's going to have to do that. And it returns a pointer to the new thing. Now the other thing that you may have noticed sitting here is that, right? In the context of defining functions, if you define a function to be static, what it means is effectively that it's private to this file. So the main program doesn't know about make node, so I can't use make node. I mean, it kind of didn't know about it anyway because it's not mentioned in lists.h, but the fact that we've defined it as static means that no other modules in a system can actually use that make node function. So in some sense, alright, yeah, as I say, the function is private to this file. Okay. So that's fine, because we only ever use make node in here. We never made nodes in the main program, either in list or in list 0. Alright, show list isn't there, and none of the functions are there, so I'll implement them all after the break in 2 different styles. Okay. So let's stop for a few minutes and then